Hey guys, I'm continuing my Worksheet 3 typers. Hopefully we get the rest of this done in one video. I'll remind you, typers, they're like more critical thinking, a little bit more like you have to use that logical reasoning to get through this. There's a lot less numbers to work through. So once again, my suggestion also, do the problems first, then come back to me, see what you do. I would go one page at a time, see what I do for the page, and then kind of move on. So this first one is asking, we've got this chart here. What if it was an XT graph? How would we solve this? So if it was XT, I'll erase the T. If it's position time, so this object, and remember you should do this on your own first, this object, this is just moving at constant velocity. And it's moving to the right. And it never changes direction. So does not change direction. Doesn't change direction. It's just moving forward. So imagine this is like a stoplight and you're just moving past the stoplight, you get past it and you keep going. So you're just moving forward. Every box you go up half a meter. So you go half a meter in 1 second. That's what it's traveling at. All right. Now, what if this was a VT graph? Now, I wish it was as simple, but something's actually happening here. So you have a linear VT graph. It actually means you're accelerating. So object travels backwards, slowing down for the first 4 seconds. And then it speeds up from 4 to 10 seconds. At 4 seconds, it's not moving. And at 4 seconds, that's when it changes directions. Now, just to be clear, you are accelerating even though you stop here, right? Acceleration, you need a change in velocity. You're accelerating the same amount each time. Even though you stop and you change direction, you're still accelerating. At some point you have to not move in order to change direction, so that's what that's showing. All right, next problem. There's a student says, faster things take less time. If I throw the ball faster, it will reach its highest point in less time. All right. So what this is saying is I throw a ball, it takes some time to reach its max point, right? So I measure how long it takes it. And they say if you throw the ball faster, it'll reach its own highest point in less time. Now, this is hard for me to explain, except I'll try to just make it more straightforward. They're kind of tricking you with this statement. Highest point? Well, the highest point changes depending on how fast you throw it. If you throw something harder, you go higher. And if you go higher, it'll take more time no matter what to reach that. So the higher you throw it, the more time it'll take. So it's the opposite. So take more time. All right, next page. Once again, you should, write this out before we work on it together. So we got a position time graph, and we got the cyclist moving. They're going to ask us, are they moving or accelerating, in what direction? So at 1 second, yes, they're moving in the positive direction. And how I know is because my slope is positive and it's not flat. If it's flat, then I'm not moving. If it's a slope, I am moving. At 1 second, is the cyclist accelerating? No. And the reason is my graph is linear. At 9 seconds, are they moving? Yes. Positive slope. 9 seconds, are they accelerating? Same thing, no. Linear. And you might see a pattern here. All right, at 4 seconds, I'm at the origin, but I am moving in the positive direction. And no, it's linear. All right, this page wasn't too bad. It's no, yes, or yes, no, the whole way. It's not accelerating at any point. It's always moving to the right. Now we'll see how complicated does it get if all I do is change it from a position time graph to a velocity time graph. At 1 second, is the cyclist moving? Yeah. And they're moving in the negative direction because I have, negative 1.5 meters per second. If each box is 1, that's what I was saying there. So negative 1.5 meters per second. All right. Is it accelerating? Once again, I'll say yes. and they ask us in what direction. So acceleration direction is, it's whatever the slope is and whatever sign that slope is. Assuming everything is like 1 meters per second up, I would say this is a gain of 5 meters per second over 10 seconds. So this guy's accelerating by 0.5 meters per second squared, and that's a positive 0.5. So yes, they're in the positive direction. At 9 seconds, are they moving? Yeah, it looks like they're moving. I go over here, it looks like they're at 4.5, or no, they're at 2.5 meters per second. So yes, they're in the positive direction. They're in the positive region. Remember, velocity time graphs are very literal of how your movement is. So if you look at the graph, that's where you are. 9 seconds, are they accelerating? So yes, and it's a constant acceleration. Whatever I got up here is the same down here. At 4 seconds, are they moving? Oh, look at that. I'm at the origin, which in this case means I'm not moving. I'm at 0 meters per second. I'm not moving. But are they accelerating? So once again, I think in the English language, we use accelerating to mean moving, but in physics, it really just means change in velocity. A moment before I'm moving, a moment after I'm moving. So yes, I'm accelerating, and yes, it's still in the positive direction. So this also applies here. All right, I'm going to move on. Looks like we're doing good time. I think we only have a couple pages left. All right, so this one, we have a position time graph. We have two of them next to each other, Ariel and Byron. And we can see here that they have different movements. And I'm just going to summarize, so answer the questions first, but I'll summarize how they're moving. Ariel is a linear line, so that is constant velocity. Byron is curving, and it looks like it's actually getting steeper. He's getting faster over time. They asked us, do either of the children ever change direction? No. The slopes are all positive. Are the two children ever at the same position along the hallway? So for a position time graph, I have to see where they cross each other. And so the answer is yes. At 2 seconds and 9 seconds. Do they ever have the same speed? All right, speed on a position time graph is based on the slope. And so basically they ask us, okay, well, Ariel is going at constant velocity. Will Byron ever go that speed? That's what this question is basically asking. Will Byron ever match Ariel's speed? Well, Byron has like a speed that's pretty close to 0 to start, but then he's speeding up over time, and he definitely ends faster. If Ariel's speed, like if we look at the average of this, Byron is starting off slower, and he ends faster. So at some point, he has to match Ariel. And as we know from before, when you're doing kind of this average velocity stuff, it's the direct middle will be the case, assuming Byron is going through constant acceleration. In this time frame, from 2 to 9 seconds, I need to think about what's directly in the middle. So, the easy way to do that, 2 plus 9 divided by 2 would be 11 over 2. So around 5.5 seconds is where it looks like they'll be traveling at the same speed. So I'm going to take like a tangent here, and that looks like a pretty much parallel line to Ariel. It might be a little bit off, but I think 5.5 seconds. So yes, at 5.5 seconds, Byron's tangent slope matches Ariel's. Do they ever have the same acceleration? And so the answer is no. Ariel has an acceleration of 0 meters per second squared. Byron's is always some positive number. All right. Any questions on that? I think we can fit in the next two in this video. I definitely want to get the next page in this video. So we have this velocity time graph. All right. This is tricky. We've seen Ariel's movement. It's a linear line on a velocity time graph. What this means is constant acceleration. What Byron is doing is not constant acceleration. This object is changing its speed. The amount its speed changes is changing. To put it into terms, like Ariel's acceleration time graph would look something like this, and Byron's would look something like this. This linear line on an acceleration time graph is not something we're used to. They ask us, do they ever change direction? So yes, Ariel changes direction here at 5 seconds, and I can tell because I'm going from negative to positive. Whenever you pass the origin, that's what happens. And yes, for Byron, at looks like 6.5 seconds. Do they ever have the same velocity? Yeah. So, I want you guys to do this first, because if I give you the answers, it's just going to go out your head. But just like how a position time graph, I could tell when they're at the same position when they cross, because this is a position time graph. So a velocity time graph, it's the same rules for velocity as it was position before, when they cross. So yes, when they cross at 2 seconds and 9 seconds. Now they ask, are they ever accelerating the same way? Now, acceleration on a velocity time graph, it's the same reasoning as before. It's the slope on these graphs, and it's going to be wherever directly in the middle it is. It looks like to me it's around 5.5 seconds again. So yes, tangent slope of Byron matches Ariel. I'm going to say it's about 5.5 seconds. So yeah, this is a very weird map. We never actually solve like mathematically problems that Byron look like in this scenario, but you should understand that these rules we've come up with, they actually still apply if in this case, we have an exponential velocity graph. It's the same rules we had for exponential position time graph. All right, I don't want to make another video, so I'm just going to do this one. An acceleration time graph, we don't have a lot of this, so let's try to work this out. A student says, to describe this acceleration graph, this motorcyclist was slowing down during the period up to 14 seconds because her acceleration was negative during this period. Are they right? Are they wrong? So this is what I'll say. Acceleration time graph. It is a very abstract graph. It kind of means one of two things. We're either speeding up in the negative or slowing down in the positive, or a combination of both. Maybe we were speeding up in the negative, but then we ended up slowing down in the positive, or you would start off slowing down in the positive and then you'd go speeding up in the negative. What I mean is, if I had a VT graph, this, or this all looks the same on this acceleration time graph, assuming these are all the same slope. So my answer is not necessarily. Could be speeding up in the negative direction. So if I just had to poke a hole into their argument, like not only could they be slowing down in the positive, they could be speeding up in the negative. All right, the last one, they asked us for instantaneous velocity, but on a velocity time graph. All right, so this is actually very straightforward. This is probably the easiest graph if you understand what it's asking for. We just need the velocity at these points, and it's a VT graph. So like this velocity is 0 meters per second. This one is 1.5 meters per second. This one's 0. This one's negative 1.25, it looks like. This one is negative I'm just going to say 0.5 meters per second. This one's 1.5 meters per second again. I'm going to say these are both 1.5. This one might be a little higher. But assuming these are equal, to finish this, B is equal to F, D, E, and then A is equal to C. All right, I'm going to cut the video off, but thank you guys, and we'll get back together for worksheet 4.